Hello all, and welcome to this second video for applications of differential functions, and in this one we're going to be looking at rates of change. Now we will look at two different rates of change. Average rate of change, so what is the average, you could think of this as the average gradient between 2 points, or the instantaneous rate of change, which is the instantaneous or the exact gradient at a single point. So this is between 2 points as average rate of change. Instantaneous is at a single coordinate. Now, the average rate of change equation is this: f of b take away f of a over b take away a, or you could just think of this as it's literally rise over run. So it is equal to y2 take away y1 on x2 take away x1, where b and a are just our x2 and x1. So again, there's nothing new here. We've been doing this already. We've also done it last year. So let's jump into some examples straight away. So for the function with the rule f of x is equal to x squared minus 3x, find the average rate of change for x being the element of numbers between 1 and 3 inclusive. So we're going from x equals 1 to x equals 3. So f of 1 is equal to 1 take away 3 is negative 2. F of 3 is equal to 9 take away 9 is 0. So it follows on that average, or the average rate of change, is equal to, what did we say that was going to be? That's going to be f of 3 take away f of 1 over 3 take away 1, which is going to be 0 take away negative 2 over 2, which is 2 over 2, which happens to be 1. That's a really nice answer. Find the average rate of change for the interval 1 to 1 plus h. So this is, while it looks a little confusing, it's still just two coordinates. The first coordinate, okay, x1, the first coordinate is 1, x2, the second coordinate is 1 plus some value h. We can still do, even though there's a h, we can still do everything the same. So f of 1 we already know is negative 2. Now we need to find f of 1 plus h. So it just needs a bit of substitution. 1 plus h all squared minus 3. 1 plus h. I'm going to expand this. So 1 plus 2h plus h squared minus 3 minus 3h, and simplify. So I get h squared minus h minus 2. So my m average is going to be f of 1 plus h, which we said is h squared minus h minus 2, take away the negative 2. Okay, that's our y2 and our y1 over 1 plus h, take away 1. So we're going to get h squared minus h on h. Look at that, we're going to be able to simplify h minus 1 over h. Cancel, cancel. So the average rate of change is going to be h minus 1 between those two points. Now, if we want to find the instantaneous rate of change, well, we need to find the derivative. So f dash of x is equal to 2x minus 3. So f dash, or at 1, is going to be equal to 2 take away 3 is equal to negative 1. Okay, so two average examples and one instantaneous. Instantaneous, pretty easy. Find the derivative, substitute in the point. Bam, there's your rate of change at that point. Okay. Sometimes, though, we need to, instead of jumping straight for the derivative or going straight for the average rate of change equation or doing a lot of work, sometimes just some familiarity with the functions will be really handy. So the volume of water in the pool balance tank is given by V of t is equal to 1 plus sine pi on t on 6, where t is time in hours and V is volume in litres. State the number of hours between the minimum and maximum volumes. Now, if we're using purely differentiation, we'd need to find the derivative and let the derivative equal to 0 to find the minimum and the maximum points. Then once you know where the minimum and maximum points are, find the x values for those points, and then do a subtraction and that would be the difference or the number of hours between. We could also graph the function, doing a bunch of work there. The quickest way to do this, though, is to recognize it's a sine function, so it's going to look like that, and between the two peaks is our period, and the time between the peak and the trough is half a period. So what we could do instead is just recognize that the period is 2 pi on n, and n in our case is pi on 6, so we get 2 pi divided by pi on 6, which is equal to 2 pi times by 6 on pi, which is just going to give us 12. So that's our period, is 12 hours from peak to peak. So the number of hours between max and min volumes is just going to be half the period. So half period is equal to 6 hours, which is equal to time as required. Just to be clear to the examiner when they're marking, because we wanted a particular time, and we're implying by saying time as required that half the period is that time. Okay. So that's all we had to do. We haven't had to do a derivative, solve, nothing. It was just recognizing the function. Now we could also find the rate of change with the volume with respect to time, though. We can do that. So we want to find the derivative. So we have two functions added together. So we just need to do sine of, so we need to find v dash of t. Well, the derivative of 1 is just 0. So we get 0 plus. Now the derivative of sine, if I think properly, sine actually goes like that. So it's going to be cos pi on 6t. And then because there's the pi on 6, if I remember the shortcut, I'm pretty sure there's a pi on 6 out the front. Now we could prove that using the chain rule. Or we can do a quick check on our CAS, calculation, differentiate. We want to do, what was it? There we go. We were doing the derivative of 1 plus sine bracket pi. Come on, calculator. Divided by 6 times by, and we're just going to change it to x. That's what it's dealing with there in the variable x. So yes, we get cos pi x pi on 6 times by pi on 6. Yeah, so that's our derivative. So we just simplify it to pi on 6 cos pi on 6t. And if you do use your CAS, make sure if you've been using x's that you give the same variable below as in the question. So there's our derivative. So find the average rate of change for, so we're finding average rate of change though, so we've got to go back. So v of 0 is equal to 1 plus sine 0, which is equal to 1. V of 6 is equal to 1 plus sine. And just to clear, I simplified this. It's just 0 times by pi on 6, which is still 0. But we get 6 times by pi on 6, which is 1 plus sine of pi, which sine of pi also happens to be 0, so we get 1. So the average rate of change is equal to 1 take away 1 over 6 take away 0, which is 0 divided by 6, which is still just 0. Find the instantaneous rate of change after 6 hours, so we need to use our derivative, so v dash of 6 is equal to pi on 6 cos 6 by pi on 6, which is equal to pi on 6 times by cos of pi. Cos of pi is -1, so we get negative pi on 6. And to be clear, since these are applied problems, we should be talking about in litres and T is hours. So we should be saying this is 0 litres per hour is the average. Same down here, this is negative pi on 6 litres per hour. We want to give units to our rate of change in applied problems. Last little bit is when dealing with motion. Now, we covered this last year, and I know a few people got confused in this, but I'm just going to go over it really simply. If you are given an equation for the position of some object, item, particle, whatever it may be, as a function of time, just like down here we have x, which is normally used for position. So we're starting with position, which is x equals some function of time. Okay. If we differentiate that, what is the rate of change of position? Well, how quickly our position is moving, we call our velocity. Okay. And just to clarify, it's technically not speed, it is velocity. And we normally give that the symbol v, and that can be some function of time as well. Okay. But that is the rate of change of position. So if we differentiate position, if we diff position equation, we get a velocity equation. Now what happens if we take our rate of change of velocity? That's asking how quickly is our velocity changing, and we do have a name for that. We call that the acceleration. Okay. So if we again differentiate our velocity function, we get some new function that will still also be a function of time, but we call that our acceleration, because that is the rate of change of velocity. So that's the connection here. That velocity is the rate of change of position, and acceleration is the rate of change of velocity. Okay, and they will all be some function of time, based on time. So, given x is equal to t cubed minus 3t squared plus 2t, so our position at any point in time is given by that equation, we can find the velocity equation by just finding the derivative of that, which is going to be 3t squared minus 6t plus 2, just using the power rule. Then we can find the function for acceleration just by differentiating the velocity. So that's going to be 6t minus 6. Bang, there we go. And that's a really, really handy and really powerful connection. So let's jump in with, we'll do this as our last example. So a particle is moving in a straight line such that position x relative to the point O at any time 10 seconds is given by the rule of this. So we're given a position. Find its position after 3 seconds. So x of 3 is equal to 3 minus 3 plus 3 squared is equal to 9, and it's in centimeters, so we go 9 centimeters from point O. The average velocity, okay, so this is an average thing, so we need to go. Ooh, let me make sure I'm going to do this quick. We want to know the average velocity. So that's the average rate of change. So let's reword this. We want to know the average rate of change of position, because that's what velocity is. So we just use our rule, m is equal to fb take away fa of b take away a. So that is going to be equal to f of 3 take away f of 0 on 3 take away 0, which we know f of 3, our position after 3 seconds is 9. Take away our position, we need x of 0, which is 3 take away 0 plus 0 squared is equal to 3. So we get 3 take away 3 on 3 take away 0. 6 on 3 is equal to 2. And again, we want to give units. So our position is measured in centimeter and t is in seconds. So that is centimeters per second. That is our average velocity, is 2 centimeters per second. Now, instantaneous velocity. So we were told previous slide that x is equal to 3 minus t plus t squared. So velocity is just the derivative of that. So velocity is equal to the derivative of x, which is equal to 3 becomes 0, negative t becomes negative 1, plus t squared becomes 2t. So velocity at 3 is equal to negative 1 plus 2 times by 3 is equal to negative 1 plus 6 is equal to 5 centimeters per second. Because yes, that was our unit. Centimeters and seconds. Okay. And then state the constant acceleration. So this is a bit of a giveaway to what happens when we differentiate the velocity, because acceleration is equal to the derivative of velocity. Okay, so the derivative of the velocity equation. So we're taking the derivative of that. So negative 1 becomes 0, and 2t just becomes 2. Okay. So our average change, or sorry, not our average, but our change in velocity turns out to be, so our acceleration, v dash, happens to always be 2. Doesn't matter what t value is, t's ended up disappearing. We know that it's always 2. And the units for this is centimeters per second squared. People doing physics, you'll be happy with that. But the way to think of this is, it's the rate of change of velocity. So velocity is centimeters per second. And then we're differentiating that again. So we're looking at the rate of change of that per second again. So it's centimeters per second, which is centimeters per second squared. So there's a couple ways you can write it. You can either write it this way, you can write it that way, or you can write it centimeters and then second with to the power of negative 2, just thinking using index laws. This isn't very common in methods, appears a lot in physics. The most common way would be this one on the left. And that's it. That is rates of change. Average is just rise over run. Instantaneous is the derivative. And there's a special connection between position, velocity, and acceleration. If you start with position and differentiate, you get velocity. If you take velocity and differentiate that, you get acceleration equation. That's it, the whole exercise in a nutshell. As always, if you have any questions, comment below or shoot me an email. Thanks and see ya.